So now we move into a chapter on Bernoulli's equation. And basically, what is Bernoulli's equation? It's basically a statement of some conservation of some type of energy. So it's an energy conservation statement or energy balance statement. If you think about energy, what do you already know about energy? Have you studied energy, different forms, and the transformation between forms? Sure. So what type of forms can energy be in that you recall? It can be in the form of internal, kinetic, potential, and then it can be transformed between forms, true? And the two transfers of energy that you've been studying a lot as a transfer is by heat and by work, especially boundary work, shaft work, either one of those. The boundary work, WB, would be the integral of PdV, how it's pushing back the face of a piston in the expansion process, or the piston's compressing the gas or something like that, boundary work, or you just have shaft work across the boundary. It could be a torque with rotational speed of a shaft, some calculation of power or work going across. But we have a lot of energy transfer devices that you studied already. What would be some of the simplest devices that you've applied the first law of conservation of energy to in your memory? Would it be something like a nozzle, diffuser, maybe a pump, maybe a compressor, maybe a turbine? There's a bunch of different devices. Heat exchangers we won't do much with because we're mostly interested in Bernoulli's equation. We're interested in the mechanical forms of energy, where heat exchangers, thermal energy, transfer of heat primarily. So we've studied a lot, and you have a lot of experience with the energy balance. So a lot of this material in this chapter is a repeat of things that you already know, but maybe it's packaged up and presented in a way that is more helpful and definitely applied to fluids problems. So what's under here? We're just talking about energy balance and how you have energy transfer in devices like the nozzle, diffuser, pump, turbine, compressor, motor. What is that? That's a device where you're supplying electric power to get shaft power. And then a generator, just the opposite, you supply shaft power to get electric power. All of these, or most of them, can have some sort of efficiency associated with it. For the nozzle and diffuser, it goes back to isentropic efficiency, and it's not as important as maybe the efficiency of a pump or the turbine or the compressor, which are also, typically they go back to isentropic benchmark. Isentropic flow of the fluid through the pump, through the compressor, through the turbine. And then what's the actual performance? And then you get an efficiency. We want to definitely know about the efficiency of the motor and efficiency of the generator, because those are introductory concepts. So if I have a motor, what's the efficiency of it? And what's the meaning of the efficiency of a motor? So Bernoulli's equation is simply a statement of the conservation of energy, but not all forms of energy, especially the forms of mechanical energy. Mechanical energy, that's organized energy. Thermal energy is associated with high temperatures of a fluid, and you think about what's temperature. It's a measure of how active the molecules are. Are they really vibrating? Are they really flowing at high kinetic energy and vibrational energies? It's high temperature, high internal energy. But that's at the molecular level, and it's very disorganized from a macroscopic point of view. So when we think about mechanical energy, it's one of these organized. So you think about Everything's going at a high speed, high kinetic energy. Everything's at a high potential in a gravitational field, high mechanical energy known as potential energy. And then this hard one, this is the hard one, flow energy. And I'm going to try and repeat myself a number of times so that you get a better grasp of flow energy with a fluid. Okay? There's something special about having a fluid under high pressure that you can then use it in a device and extract energy out of it, the flow energy out of it. So that's like the pressure is associated with the mechanical energy of the flowing fluid. And then to make things not only complicated because we're thinking about 1, 2, 3 types of mechanical energy of a fluid, especially as it flows, we can also think of talking about that energy just on a per unit mass basis, on a per unit volume basis, and even the hard one, the per unit weight basis. Okay, the fluid has some mass, so I could talk about its energy per unit mass. That makes sense. The fluid has some volume, so I could talk about the energy content of that fluid per unit volume of the fluid. That makes sense. The one that really doesn't make sense to you probably is the energy per unit weight. Well, why don't I just talk about either per unit mass or per unit volume? Because the textbooks all over and fluid mechanics are all over where you're talking about the energy per unit weight of the fluid. And that's actually one of the most common ways to talk about it. It's called the head. Head. All right. So what do I have under this box? Well, it's a long chapter. Let's not get too psyched out. Let's just kind of go through it. But when you get Bernoulli's equation, you can also go and get Torricelli's equation or Torricelli's law. He developed it before Bernoulli's equation was established, but it's a statement or restatement of Bernoulli's equation for a particular problem. We can understand Venturi effect, Venturi meters, and there's a lot of those out there. We can understand the pitot tube, the pitot-static tube. We need to understand that coming out of this class. That needs to be like if somebody said, oh, you passed fluid mechanics. You know, I took fluids and I really never understood the pitot-static tube. Can you please explain it to me? At that point, rise and shine, right? You can do it. Siphoning. We should be able to understand and describe mathematically siphoning. There's a lot of applications of something as simple as that. Then we have some other factors down here, the kinetic energy correction factor, which is in this textbook. It's in a lot of textbooks, but it's not. A lot of times people just assume it's one and run with it. Assume it's unity and run with it in the equation, but we'll beat you up in the details of what that is. And then we modify Bernoulli's equation to account for losses. Where does energy get lost? How does energy get lost? Well, in the bookkeeping, it goes out of the form that we want to keep it in. We want to keep it in a mechanical form, one of the three mechanical forms of either high pressure, high speed, high elevation, speed. You can think of the flow energy as pressure. And how does it get lost? Through friction. It's friction. So it goes out via dissipation. That's a great loss. And then sometimes you can gain or have an increase in the energy of the fluid because there's some work coming into it in the system. So maybe you're looking at having a piping system and then there's a pump in there, and the pump is increasing the flow energy of the fluid. So you could talk about head gains or head losses. Long chapter, it's an important chapter. Let's keep going. So what is the purpose of a nozzle? Somebody says, describe to me a nozzle. And everybody should say, yeah, I've heard of the word nozzle. I've analyzed nozzles. I've solved problems, nozzle problems. What does a nozzle do? So typically a subsonic nozzle, decreasing area, cross-sectional area in the direction of flow. And then what happens between the inlet 1 and the outlet 2 of the flow of the nozzle? something, what happens to the pressure? Does the pressure stay the same, go up, go down? It goes down. And what happens to the speed? Go up, it goes up. So basically, the nozzle is a device that converts between two forms of the energy. It's going to decrease in pressure and increase in speed, which is increase in kinetic energy. And so if you want, you can say, well, the nozzle really takes that pressure, which is a form of mechanical energy, and converts it to kinetic energy. That's what the nozzle does. What does a diffuser do? Diffuser typically has a smaller inlet area, larger outlet area, inlet 1, outlet 2. What happens to the speed? Goes down. So a decrease in the kinetic energy. What about pressure? There's actual pressure recovery. And this is a crazy thing about diffusers. There are cases where you do have flow from an area that is lower pressure into an area of higher pressure. Most of the time, flow goes from high pressure to low in a duct or a pipe or some system like that. But there are cases where you have flow going from a low pressure to high pressure. Does flow like to go from low to high pressure? No, it's like pushing a rope. If you try to push a rope, what's it trying to do? Curl up? It doesn't. You can't push a rope very well. You could pull a rope well. Fluid likes to go from high pressure to low pressure. That's like pulling a rope, but to go the opposite in a diffuser. So diffusers typically don't rapidly expand in the area, do they? They're very gradual increase in the area. Where if you look at the angle at the rate of change of the area for a nozzle, it doesn't need a long distance to do that. It can be a pretty severe decrease in area in the direction of flow for a nozzle, but for a diffuser, often they're very long and very gradual increases. Okay, so that's our diffuser. What about a water pump? That's a pump. Often we just say, here's our image of a water pump. It has inlet and outlet, inlet state 1, outlet state 2. What do we supply to the water pump to make it work? A shaft. So we have some sort of shaft work or shaft power. W.SH, we do a little control volume analysis around it. And let's say it's a water pump. Did it increase the density of the water? Did it change the density? No, it didn't do that. So what's it doing? Is the mass flow rate coming in at 1 different than the mass flow rate going out at 2? Did it increase the mass flow rate? No. No. These are the type of questions that trip students up when they first analyze a pump, right? And they're like, oh, it doesn't do that. It doesn't change the density. What does it do? It changes the pressure, and that's the key idea. What is the pressure a measure of? We're going to beat that in a couple slides. But guess what pressure is? Right away you're saying, that pressure is some sort of mechanical energy of the flowing fluid. So we have shaft power goes into fluid power. How is it realized in the fluid? Increased pressure, not increased flow rate. Not decreased density or increased density or anything like that. Okay, now we get to a compressor, which is different than a pump. What was the big difference between a compressor and a pump? The density is not necessarily the same on inlet and outlet. Because of the pressure change, you can be more dense. So when we think of a compressor, there's 2 types of compressors we analyze to death. One is an air compressor, one is a refrigerant compressor. Those are great areas of application. So you'll say, okay, for a compressor, we have either an ideal gas, like air, or we have some refrigerant that's just saturated vapor or slightly superheated vapor, but it's close to the dome, and we can't treat it as an ideal gas. So sometimes we treat the fluid as an ideal gas, in the analysis of a compressor, but sometimes we can't. Okay. But the purpose is you feed it shaft power, and what does it do? It increases that flow energy. But now it's more than just pressure alone. It's going to be kind of a PV term. Do you remember that in our energy balance? A pressure volume term. Because it's changing pressure, yes, but also the specific volume or the density, the reciprocal of the specific volume is mass density, is changing as well. How about a turbine? Well, this one gets more complex for students because it's not just one type of turbine. You can have a gas turbine, like in a jet engine. You had the expansion of the gases after the burner. That would be a turbine section of the jet engine. You treat it as ideal gas like air, and you can do a pretty good analysis of that. You could have a steam turbine in a power plant. Don't necessarily treat that steam like a ideal gas. Absolutely not. Stay away from it. Treat it using the properties and the steam tables, because the fluid doesn't behave as a true ideal gas as it flows through the steam turbine. And then you have a hydraulic turbine. What is that? Hydraulic turbine. It's liquid water. We don't have many dams in the state of Texas, right? What states in the United States have a lot of water generated electricity, hydroelectricity, hydro plants? Nevada, do they have that with whatever dam that is? Hoover, yeah. They can generate electricity out of that one. Anybody lived in the great state of Tennessee? Lot of hydro generated in the Tennessee Valley Authority, TVA. And then up in either Oregon or Washington State, I forget which, that area has a lot of hydroelectric. Okay? So there it's liquid water in from the bottom of the dam, which is high pressure, and then out at atmospheric pressure at the discharge. It stays liquid, and so it's a hydraulic turbine. Okay. There you're trying to convert that fluid pressure flow work, that PV, if it's a gas or steam or just P, into from the mechanical into the shaft power. There's other energy conversions. These all have the fluids flowing through them that we are familiar with. What other energy conversion that I talked about on the previous slide? You just have a electric motor and you have electric generator. So you have electric power coming in and shaft power going out, or shaft power in, electric power out. They all have efficiencies. These we definitely want to make sure we have understand and work with efficiencies on those as well as the other ones. But what is efficiency of the generator? Generator efficiency, that would be the electric generator, this one right here. It's the efficiency of the generator is what you desire. Some W dot electric out divided by W dot shaft provided, the power of the shaft provided. And then electric motor, just the reciprocal. Turbines, compressors, pumps, and we're going to skip the nozzle and diffuser efficiency, but these other ones you should be familiar with and how to calculate them. Not all of the energy, this is the key idea, not all of the energy stays in the form that you want it in. You want it in a high value form of the energy. Electric power, extremely valuable. Mechanical power, extremely valuable. The fluid power that's in the high pressure, high speed, high elevation, extremely valuable. And then sometimes it gets transformed in between forms, and sometimes there's a friction, dissipation. Some of it's lost out of the mechanical and into heat and thermal. So we have a lower than 100% conversion efficiency. What is kinetic energy? I'm going to not do too well in this class if we don't have a very firm grasp of kinetic energy. So I'm going to stop. I want you to write down what is kinetic energy on your sheet of paper, because watching me tell you what's important isn't as important as you being able to tell yourself and remember and recall. Okay, what is kinetic energy? All right, so a lot of people wrote that the kinetic energy can be described as 1/2 mv squared. You know what? I don't think you derived that equation, did you? I don't think you derived. I think you recalled that equation. Could you rederive it? It'd be a challenge. You have to go back and look. How did we rederive that? But it's one of these where once you derive it, start using it, you just kind of recall that equation. So it's the energy associated with the speed of the object. Now, some people wrote that it's just the speed is proportional to the speed squared, but it's also proportional to the mass of the object, isn't it? If you have a larger massed object, doesn't it have higher kinetic energy for the same speed? Sure. So that's what the kinetic energy is. It's a form of mechanical or organized energy, and it's 1/2 mv squared. Could you do this? Could you write the kinetic energy? Let me do this. What are the typical SI units for this KE that I just shown right here? What are the typical SI units for this kinetic energy? Is it meters per second? Is it meters? Is it, joules? What is it? Is it Newton? It's a joule, isn't it? Or maybe we work in kilojoules. Joules or kilojoules. Just watch out for that factor of 1,000. You can get make an error on a factor of 1,000 with the kilo in front of something. How do we get a kilojoule? Well, put in a kilogram, put in a meter per second and a meter per second. Did I get the meters per second squared? Okay. So what is a Newton? Is that a kilogram meter per second squared? Did I do that one right? So the second squareds go, kilogram go, and one of the meters go. And then what's a joule? Is a joule a Newton meter? And so then we're getting rid of the meter, get rid of the Newton, and we're left with the joule, unit of energy. Okay. Could I express the kinetic energy of this object of mass m as per unit mass? This seems like a silly question, but could I express the kinetic energy per unit mass? What would it look like? Well, maybe we take the large KE, kinetic energy, which is in joules or kilojoules, and we divide it by lowercase m. Well, what is that? Maybe a lowercase ke, this is uppercase ke. Maybe you're familiar with that terminology coming out of thermodynamics. And this lowercase ke is just 1/2 v squared. So it's a energy per unit mass. So what would be the SI units? Thinking of SI units over here, what would be the SI units of the lowercase ke? Kilojoules per kilogram. True or false? Yeah, that makes sense. Kilojoules per kilogram. So here's another one. Let me move it over here. Can we talk about it per unit volume instead of per unit mass? What would that look like? Well, here, instead of Ke per unit mass, I'm going to make up the symbol Ke per unit volume, lowercase ke underscore VOL for, so we're going to add the kinetic energy per unit volume. What is that cap V? Volume. Just like M was mass, V is some sort of volume. What would be the units? Kilojoules per meter cubed. But if you take a look at it, you have 1/2 m over v, that's volume, v squared, velocity squared. So one v is for velocity, one v is for volume. Sorry about that, but that's life. That's fluids. But what is this term right here? Mass divided by volume. It is the rho. That's exactly right. It's 1/2 rho v squared. How many people have seen 1/2 rho v squared somewhere before in their prior life? Yeah. We're getting the Bernoulli's. 1/2 rho v squared. We're getting the Bernoulli's equation. So what is this? This 1/2 rho v squared is kilojoules per cubic meter in SI units, isn't it? But what is a joule? Could I convert the joule to Newton times a meter? Is a joule equal to a Newton meter? Okay. So could I also express this 1/2 rho v squared as a kilonewton per meter squared? Does it have the same units? Is that the right units? Can I do a little name calling? I say, oh, look at this, kilonewtons per meter squared. That looks like a pressure. A pressure. That looks like pressure. All right. So this looks like energy per unit mass. This looks like pressure, but pressure looks like energy per unit volume. And I'm going to repeat myself again and again on that. All right. Before we jump off, let's talk about potential energy. Somebody says, I forgot the equation for the potential energy of this object of mass m. Can you please tell me what is the equation for the potential energy? Do you recall? So cap PE is equal to mgz. So if you don't have a gravitational field, do you have potential energy? No. But we know that the higher you are in a gravitational field, with increasing z elevation in a gravitational field, it has higher and higher potential energy. And it's proportional to the mass. What would be the typical SI unit? Yeah, it would be the same thing. You're saying, prove it, because I don't believe that a mass times g times z gives me the units of joules or kilojoules. Well, let's prove it real fast. So what about a kilogram for mass? Meter per second squared for, is that true, for g? And then we have meter. And then you say, what is a Newton? Is a kilogram meter per second squared? The meter squared, second squared go, kilograms go, one of the meters go, and then I have a Newton times a meter, and a Newton times a meter is a joule. So yeah, we get joules. We get joule with a K or without a K. You just have to worry about that thousand. So the SI units are something like kilojoule. So I didn't uncover that box on the other one, but that's all. We're just confirming that the potential energy is mgz. Well, what do you think's under this box right here? Can you express the potential energy per unit mass? Can you talk about its mass density? Well, let's take the cap PE and divide by m. We'll call that a lowercase pe. Maybe you want to put a underscore MASS on it, because it's going to be the lowercase pe, the potential energy per unit mass. And when we do that, we just find that that's just GZ. Hey, I think I've seen that GZ around before. Thermo 1, you wrote it so many times you probably are tired of writing it. But what is GZ? Potential energy per unit mass. And then what could we do? Because a lot of times we work with flowing fluids that have not only mass, but we have mass per unit volume, or we have the volume of the flowing fluid. We could talk about the potential energy per unit volume, which would be the potential energy divided by the volume, which is mgz divided by the volume. What is the mass per volume? Rho g c. That looks very familiar. We just came out of fluid statics, didn't we? Somebody says, here's a fluid tank, and I want you to get me the pressure at this distance. You say, okay, you're just going to have to tell me that depth at which it's beneath the free surface. And what will the pressure at that, in that tank of static fluid, what will the pressure at this distance be? Rho GH. Look at this. Rho GZ. That is very familiar, isn't it? But we're talking about potential energy per unit volume. Okay, let's do this. We had the SI unit for cap PE, it was kilojoules. What is the lower SI units for lowercase PE, potential energy per unit mass? Kilojoules per kilogram. How about for this potential energy per unit volume of the fluid? It'll be kilojoules per meter cubed, which we already did. What is it? It'll be something like a kilopascal, right? Let's go back. What is a kilonewton per meter squared? Is I forgot to say it, didn't I? Sorry, kilopascal. It's a pressure. It's a pressure. So you're thinking, we can describe the potential energy per unit volume, and it'll have the same units as pressure. It'll be energy per unit volume. Okay. Ready to go to the hard one? What is pressure? First answer, what comes to your mind? Somebody says it's force per unit area. So we're going to talk pressure is equal to the force, the normal force acting on any imaginary or real surface, per unit area of that surface. That's that fluid pressure. It's a normal force. Okay. So what would be the typical SI units for that? Pascal, which is, well, I'll put a kilo on there. It doesn't matter, but which is a kilonewton per meter squared. Okay. Somebody says, what is the product of a force times the distance? Force, and you have a distance moved and it's in the same direction as that force is being applied. It's work. It's work. Isn't that work? Okay. What is if I have an area and I move the area perpendicular distance? Sweeping. It sweeps the volume, doesn't it? So you can see that the pressure is not only a force per unit area, but when I multiply it by 1, distance over distance, distance in the numerator, distance in the denominator, I pick up work, which is going to be some sort of increasing mechanical energy or decreasing mechanical energy, depending if the fluid's doing work or receiving work. But it's organized energy transfer. And then what do I have here? The volume. So when you see pressure, right away you can say, aha, pressure is the force per unit area. But it also can be interpreted, especially in a flowing fluid situation, as some sort of energy per unit volume. Mechanical energy per unit volume. So let me uncover the same things that I just talked about here. Okay, well, my computer will obey me. And then, so what do we pick up for pressure? It's energy per unit volume. That's probably new to you, right? That you can think of the pressure as the energy of the flowing fluid mechanical energy of the flowing fluid, that because it's associated with the flow work when it changes pressure going through the device or across the device. And you have the energy per unit volume. Well, what did we do before? We said we worked on the SI units. We found that it's kilopascal, kilonewton per meter squared. But how do I get it to look like an energy? Well, if I multiply this by a meter over a meter, get rid of that. If I multiply that by a meter over a meter, doesn't a meter squared times a meter give me a meter cubed? That looks like a volume. And what about the numerator? Kilonewton times a meter. A newton meter is a joule, so it's a kilojoule. So the pressure has the units of kilojoule per meter cubed. That's the same as a kilopascal. But we then say, take the pressure and now divide it by the mass. I want this pressure divided by the mass. Let me just leave it as P over M. What does that look like? Well, look at their SI units. You'll have kilojoules per meter cubed. Well, let me do this. Let me uncover. Get this down here. Maybe not mass by itself. Divide it by mass per unit volume. Do that. Mass per unit volume. So this is pressure divided by the density, mass density. And if we chase our units, we have kilojoules per meter cubed for the pressure. We divide it by the mass density, kilograms per meter cubed for the units on that. What units? The meter cube cancel, what are we left with? Kilojoules per kilogram. So when we see this ratio of pressure divided by mass density, it's energy per unit mass. It's the mechanical fluid energy per unit mass. All right. Let's do the next one. If I have it per unit mass, maybe I also want to be able to express it per unit volume. But what did we say pressure was? Pressure is the energy per unit volume. It's already there. So when you see pressure, you can think of energy per unit volume, and that's very, very handy. A pump increases the pressure of water. So here's the pump. The pressure of water comes in at 100 kilopascal. Is that a good unit for pressure of water? Goes out at 900 kilopascal. Okay. Somebody says, what is the increase in pressure across the pump? 800 kilopascal. Right? Okay. The next question is what is the mechanical energy increase per unit of mass of the water? Express the answer in kilojoules per kilogram. So we're going to have a change in the energy of the fluid per unit mass of the fluid, and we want that answer in kilojoules per kilogram. Well, how is the energy, mechanical energy, realized? It's either through an increase in the kinetic energy or the potential energy, or this flow work energy, this mechanical, this flow energy. All right? Was there an increase in kinetic across the pump? No. Potential across the pump. The only thing it did was increase its flow energy realized by an increase in pressure. It seems so trivial, but it's not trivial. It's pretty complex conceptually. So how do I calculate this increase in energy per unit mass? Well, I say that if I knew the change in the energy per unit volume, then I could multiply the volume per unit mass. I'd have this problem solved, wouldn't I? And guess what the energy change per unit volume is? That's the change in the pressure. Then we multiply by the volume per unit mass, specific volume. The specific volume of water. Somebody says, I need a textbook to tell me that. No, you don't. Give it to me. 0.001 meters cubed per kilogram, isn't it? If I have one liter of water, that's 0.001 meter cubed. There's 1,000 liters in a cubic meter of water, or just in volume, forget about it. It's 1,000 liters per cubic meter, true. And 1 liter is 1 kilogram. That's I can remember that. Okay, so the specific volume of liquid water. So I take that delta P of 800 kilopascal, and I might as well say a kilopascal is a kilonewton per meter squared. Did I do that okay? Multiply that by 0.001 meters cubed per kilogram, and what do I get? I get a kilonewton times one of the meters left over. That's going to give me a kilojoule per kilogram. So what is the best answer? A, B, C, D, or E? A. The best answer is 0.8 kilojoules per kilogram. What happened here? I increased the pressure of the flowing fluid through the pump. It increased the mechanical energy of the flowing fluid by 0.8 kilojoules per kilogram of the flowing fluid, water. Ready for a harder question? What do you think we're going to do? Tell me, what is the mechanical energy increase of the flowing fluid per volume of the water? Not per unit mass of the water, per volume. My answer needs to be in kilojoules per meter cubed. Let me pause and let you work on that.